Welcome to video 4 of our series on solar heat for industrial processes called SHIP. This is developed within the UNIDO project Greenhouse Gas Emission Reduction in Targeted Industrial Subsectors through energy efficiency and application of solar thermal systems in Malaysia. My name is Jürgen Fluch. I'm head of the Department Industrial Systems at IEE Institute for Sustainable Technologies, located in Austria and being one of the leading research institutes in solar heat for industrial processes worldwide. Together with our team, we have supported the UNIDO project as international experts along the whole project phases. You already heard about the potential of solar heat for industrial processes worldwide and specifically in Malaysia, the necessary energy assessments and the best practice examples worldwide. SHIP is a state-of-the-art technology well proven and operating since decades, but it is mandatory to follow a clear methodology for the optimized design to ensure that you are happy with the solar system at the very end. Tick in your mind the checkboxes when you have already achieved this in your company or your project. You have done an assessment on the industrial energy system. Data is available and a company visit was done. Don't get me wrong, but you can't work on something you have never seen, so designing by doing. You know about the load profiles of the energy demand, a 24/7 production or only one shift from Monday to Friday, significant variations over the year. We have to consider this. How efficient is the existing supply system? We have to know about real performance and not only the full load operation. In most cases, there is a huge difference. As we heard in video 2, we want to decrease the energy demand first. So energy efficiency is the first fuel. And we don't want to pay for something we don't really need, right? So we optimize processes and we make use of excess heat. Well, a natural gas boiler needs space, so do solar collectors. We have to be honest, solar collectors need a bit more space than a boiler. But we use your roof and available space on the ground. And we have to identify the optimized integration point of the SHIP system. No worries, this is standardized and experts worldwide have developed this methodology by 2014. As said, this is a proven state-of-the-art technology. And having all this done, we start with the design of the solar thermal system. So what is the SHIP system about? It is not only the collector, but of course the collector is the centerpiece. The sun heats up the fluid inside the system. This can be water, oil, air, whatever you need or depending on the energy demand you have. With the hot medium, we load a storage tank. So this enables the possibility to cover the energy demand in times when there is no sun shining during the night or when there is some rain, for example. So by discharging the storage tank, we deliver the energy to the industry and if necessary, we integrate a conventional backup system and in most cases, this is already there. Looking at the world map, we see areas in almost all colors: red, yellow, green and a bit blue. If you are located in a red region, it is obviously hot and you can harvest a lot of solar energy. I'm coming from Europe and you see that we have mainly green areas there, but we have a very, very high number of successful and economically feasible operating SHIP systems. Why? Because the experts just did a great job. Being lucky living in Malaysia, not only that it is a great country I love to visit, you have plenty of solar energy with almost red areas. So spot the place where you are and you see how much energy there is for free. As said, we need some space for placing the solar thermal collectors. Do you have some roof space? The expert will check the static conditions. Is there space on the ground? Even better, and don't be worried, there will be a lot of plants growing around the collectors. The good thing in Malaysia is it makes almost no difference how your ground or roof is oriented. As a result of the energy assessment, we know all details about the status quo of the energy system. In the example, we see 3 processes operating at different temperature levels being supplied by a centralized hot water pressurized system at 130 degrees Celsius and a return temperature at 110 degrees Celsius. We see in our example that the 130 degrees Celsius system is supplying processes with a heating demand at 50 degrees Celsius only. The result are high losses and a pretty inefficient system. Basically, we have now 2 options to integrate the heat coming from the SHIP system. The easiest way is to do it on the supply system level. So we connect our pipes to the existing system. We install a heat exchanger, heating up the return flow completely or partially from 110 degrees Celsius up to 130 degrees Celsius. So we need one heat exchanger, simple integration, all processes are supplied and we have no changes in the processes. But there is one disadvantage. The higher the temperature from the solar system, the lower the efficiency of the collector is. So this is a trade-off between system complexity and the efficiency of the collector. The second possibility to integrate the ship system is on process level. So we specifically design the system for the most feasible processes and by this increase the efficiency of the collector. In our example, these would be the processes operating at lower temperatures. This might lead to 2 or more separate solar systems, 2 heat exchangers, one for each process. So the system complexity increases, but the efficiency of the collector and the whole system is significantly higher. In both options, the impact is a reduction of the energy demand supplied by the boiler, the energy costs, the CO2 emissions, and the dependency on external energy supply. Having this draft system designed, we optimize it, maximize the yield from the collectors, we minimize the heat losses, we optimize the system efficiency, and we avoid malfunctions as, for example, stagnation by a standardized control system. We vary the sizes of the collector, of the storage tank and the heat exchangers, and with this optimize the whole system. Standardized tools perform system simulations based on the design concepts, and we are highlighting there, for example, the yield from the ship system, loading the storage, discharging the system and providing energy to the processes. The result is the optimized system design ready for implementation. To summarize, ship is not rocket science. It is a state-of-the-art technology but needs a clear methodology to be designed. You perform a detailed energy assessment beforehand, implement optimization measures to reduce the energy demand. And based on this, you design and optimize the ship system. Including the economic and ecologic assessments, this is the basis for the approval by the top management, so they will be really happy if you have done a good job. Implement the system, do a proper monitoring to see how efficient your system operates and optimize it if necessary. And the result is a reliable and sustainable energy supply system. You are not the front runner worldwide going for solar heat for industrial processes. There are hundreds of successful implementations worldwide, and within our project we gained interest in Malaysia, and now we have several well-operating systems designed by trained and certified experts. These are only some examples. Join the solar thermal community. My name is Jürgen Fluch, and as one of the international experts of the UNIDO project, I am looking forward to supporting you and answering your questions together with my team.